Okay,
everything.
Gerhard, I will not repeat, and I'm very happy to welcome you for this inspiring presentation. So please, the floor is yours, Gerhard.
Thank you. And thank you, Jean-Pierre, for this friendly introduction. And I want to welcome everybody. And of course, as I mentioned, we had a little rehearsal. And in the rehearsal, I already smelled India. And I'm missing that. So sorry not to be there in person, that we have to make this a virtual event. I'm really looking forward to my next visit again, where I can be live in India and we can sit down and enjoy personal discussions. Anyhow, so thank you, everybody. I will talk about an idea of mine. I call it the 6G Gearbox PHY idea, physical layer idea. PHY, as many of you know, stands for physical layer. So now, if we think of that, what is it that we need to do? We have, obviously, going from generation to generation, we have higher data rates. Yes, we have the red line, which is cellular, and we have the blue line, which is Wi-Fi. And if we look at these two lines, we see the blue line got a dent. At a gigabit per second, after that, it did not really increase 10x every 5 years, which is doubling every 18 months, which is Moore's law. It got a little bit slower. And the reason why it got slower is mainly because of power consumption. So if you look at Y gig, Wi-Fi 5, Wi-Fi 6 with a AC and AY, extensions in the 60 gigahertz range, we have data rates available which basically extend the blue line as if it was continuing to have this traditional exponential growth. But what has happened is we have been hit by the power consumption. And so now the question is, as 5G is reaching into this domain of a gigabit per second and beyond, will we also be hit by this power consumption, or what is it that we can do? So we really have to have a look at this and understand why this bend is happening, because the applications I'm showing here, my PhD student, Tobias, and former PhD student, and the virtual reality, augmented reality areas, they really need high data rates. Yes, I mean, every goggle needs a gigabit, 10 gigabit per second to have high def 3D, augmented, and virtual reality. So it is not that we don't need those data rates. And if you think of wireless being a shared medium, we need a ton of that. So we could even eat up a terabit per second if, however, we had the power consumption somehow under control. And today, the technology with the power consumption is not there. Instead, what do we see? We see that this is Samsung's, Huawei's, Oulu's, many people's view. I can show plenty of these kind of spider diagrams where people say, or companies state, we really have to increase every single performance measure of 5G into the next kind of area. The data rate, the energy efficiency, spectral efficiency, latency, connection density, reliability, peak data rate. I'm not quite sure. Because yes, I mean, obviously there's a good reason why we in HANA have user experience data rate to be increased. But do we really have to increase beyond Moore's law? If you look at this, the peak data rate is now proposed, for example, to increase suddenly not 100x in 10 years, but 1000x. So outperforming Moore. And this is difficult because we are bound by semiconductor technology. However, there are certain parts also where we certainly don't need an improvement. Reliability, latency, spectral efficiency. I will not dwell in depth on that. I have talked about that in plenty of keynotes in 2021. But all I can say is we can show that with the technologies that we have, we really don't need that to increase the reliability, latency, and spectral efficiency more. This is not what 6G is about. But what we really need to do is increase the energy efficiency, yes, and way beyond just a little bit. We really need a massive improvement, because going from 4G to 5G, our networks don't need the same amount of energy, but typically 3 times more. And so a 2x improvement is not enough. We want to be even more environmentally friendly. We want to not only keep the energy level, but we want to reduce the energy level dramatically over 6G. We want to reduce it even possibly beyond, below that what 4G was. And we need trustworthiness. Trustworthiness is really important. We need trustworthiness. We need also integrity. We need to be resilient against radio attacks, radio interferences. We have to think about being cost efficient, meaning joint communication and sensing. And with communication controlled co-design, we have shown that we really don't need these 2 parts. We can really get rid of that. So that means, okay, now what is the issue? We have a yes on spectral efficiency. No, we have a no on spectral efficiency, but a yes on energy efficiency. And this basically means that is doable. But if both were to be increasing, I don't know any physical law that allows us to be even higher in spectral efficiency and more energy efficient. So this is something where there is some problem here in this graph. And this is where I want to talk about this. Now, in the context of where we are, where is 5G and 6G going to be? Yeah, first generation was analog. It was voice communication for business customers. Yes, these analog phones were typically too expensive for private people to be able to pay for them. 2G made it a consumer product. So suddenly, from 10 years of business telephony, mobile telephony, we went to 10 years of consumer mobile telephony. Then we introduced data. Data was a big step function in 3G. And in 3G, first we had the business smartphone, the BlackBerry and the Nokia communicator. Then we had the consumer smartphone. And this consumer smartphone started with 3.5G, but really took off with 4G. With 5G, we again have a new step function. The step function is tactile internet, remote control of virtual and real objects, augmented and virtual reality just being one of it. That means here, if we look at what's happening in 5G, I'm running 9 testbeds. And in these testbeds, or the 5G lab is running 9 testbeds. And in these testbeds, we have campus network. We're doing driving, we're doing agriculture, farming, we're doing orchards, we're doing wineries, we're doing flying, construction industry, logistics, factory automation, all these different use cases, none of them being consumer. So again, if we look at it, if we really think of what this ultra reliable low latency communication of 5G is about, there's really new part in 5G. It's about addressing business needs. And with 6G, we want to be able to make this consumer ready. And everything of it, 1G was clunky, energy inefficient. 2G made us the small, sleeky smartphone that we loved and put in our pocket and was cost effective. 3G was super energy inefficient as it was introduced. Remember, there was a huge energy problem and expense problem. And in 4G, this became a consumer product. Again, in 5G, if we look at these new applications and what is needed, the way it's done right now, it is not on the cheap side. So we have to do something to make this really consumer friendly. So cost down, cost down, cost down, cost down. And if we mean cost down, we really mean cost down. And cost down means obviously different parts. And I want to talk about a couple here. I will only quickly touch on sustainability, meaning cost down, meaning resources of spectrum and functionality. If we think of mobile robotics and augmented reality as well, we want to do gesture detection. And mobile robotics, we need a lot of sensing as these robots move around. It's not only about connecting to the device. This device also has to do a lot of RF sensing. And so the question is, do we really want to stay with the current approach of having separate spectrum for radar and spectroscopy and separate spectrum for communication, or don't we want to do this in a joint fashion? And the joint fashion is really the way to go. There's now the second IEEE Symposium on Joint Communication Sensing coming up in March, in a couple of weeks. And it's picking up a lot of speed, this topic. And this is really something where we can see that things will be going such that we can already have a very cost-effective solution so that you don't have to buy a separate radar system, because the radar is going to be done also with the communication device, as an example. The other part is energy. And I really want to talk about the energy efficiency here now. And this is to be found in a paper that was the feature article of the inaugural issue of the IEEE BITS, the Information Theory magazine. And it is something where I really think I would like to take you now and make sure that you understand what I'm talking about. If we want to increase the data rate, and I mentioned the data rate is an issue. Today, we design everything for full buffer peak data rates. And what is really the energy bottleneck in that case? If we think of that, we always think of what is the peak data rate? What can we deliver in this kind of thing? And it is the A to D converter in the future. Why that? If you look at it, what we have is the energy of the A to D converter has been sketched here by Boris Merman and his team over the years. And you can see here, this is the energy efficiency of an A to D converter, and the x-axis is the sample frequency, and the y-axis is the conversion steps. And there we have the figure of merit telling us what is going to be happening. If we look at this from 97 to 2009, you get the blue dots, and 2010 to 2020, you get the red markers. And these blue and red markers clearly have an outskirt. Yes, the energy efficiency of A to D converters has been increasing. This is 11 years, and if you factor this into 10 years, about by a number of 33 in the last 10 years. This has given us the benefit that the A to D converter was always a small part in our energy budget, and it has not been reduced by 100x, but not that much far away from the 100x, so that we really didn't worry too much about the A to D converter. Why is there an issue now? Yes, the issue is that the next 10 years, we see that only 1/10 is going to be given to us by process technologies, by what we see in the next technology nodes. If that is the case, and one other thing that you can see here, which is really important, is there's a need around 200 gigahertz sampling frequency. Suddenly, our energy consumption is not linear with sampling frequency as it is here, but it starts being a square law. So if we increase the sampling rate by 10x here, we actually increase the energy of the A to D converter by 100x. What does that mean if we look at this table? Let's see where we are. 2G at a bandwidth of 200 megs, 3G of a little more than 2 gigs, 4G 20 megs, 2 megahertz, 4G 20 megs, 5G 200 megs, a typical channel bandwidth, which means we haven't seen sort of an average increase of a channel bandwidth of 10x. At 10x, the question is, we're going from 200 megs to 2 gigs. And I made a mistake here when I said 200 gigs. This is 200 megs. Yes. So at 200 megahertz, we have this nonlinear energy efficiency. So now if we go from 200 megs to 2 gigs, we have an issue. This 10x increase in power consumption gives us 100 increase, the 10x increase in rate gives 100 increase in power consumption. Then comes in addition that we need more resolution steps for every generation from generation to generation. This gives us typically a 10x increase in power consumption. And we typically have had a 10x here, a 10x here, and this has been compensated sort of by Moore. But now this is not in total at 100x, but it is in total 1000x. And we are at a technology point in time where Moore is only giving us a projection of 10 times improvement. That means 1000x power consumption in projection from a technology compensation point of view remains to be 100 times power consumption. And this is an issue because if you think of a handset, the typical power consumption is in the realm of 100 milliwatt. So going from 100 milliwatt to 10 watts, we're really talking about an issue. 10 watts means it's the dominating part on the transceiver in the handset. In the base station, the whole thing is increased, of course, by a couple orders of magnitude, but the relative power consumption is very similar, and therefore suddenly also the A to D converter at the base station becomes a dominant part because it has also a couple more steps resolution, of course. Now, if we look at this and say, okay, what can we do from a communication point of view? We have Shannon. And we have Shannon, and capacity increases with the number of MIMO streams, the bandwidth, the antenna gain, and the signal-to-noise ratio in this kind of capacity formula. And if we look at this formula, this basically also holds for Rayleigh fading channels and Rice fading channels. So it's a little different. It has a factor in front, but still Shannon gives us this capacity. Now with this, that means suddenly what? This means what can we do when we want to reduce the power consumption of our system? We can go from turning off modems in antenna beamforming, massive MIMO beamforming, in digital beamforming, or we can increase the M. Whatever we do with the M to increase the data rate, we have this exponential dependency here with the log. And if we want to reduce it, we only get the logarithmic benefit. Same thing in the SNR. If we say we want to go to lower SNR regions, we can only get the logarithmic benefit. If we want to reduce the number of MIMO streams, we get a linear benefit. If we want to reduce the bandwidth, we get a linear benefit. So think of it this way. Now we want to not think of reducing, but we want to increase the data rate. We want to increase the data rate, and we have basically two bounds. Yes, upper and lower bound, doesn't really matter. It's pretty much this linear logarithmic kind of thing, and the lower bound is just linear. And if you look at it, this means no matter if we look at low SNR and everything is in a linear domain, the power of the ADC still goes exponentially, even though it's linear, no matter what we do. And why is that? If we parameterize the signal-to-noise ratio. If we increase the signal-to-noise ratio, even in this kind of setting, we have to make use of it with a higher constellation size. A higher constellation size means our constellation goes exponentially in complexity. And as it grows exponentially in complexity, the A to D resolution has to grow exponentially too, exactly with the power of 2 to the R, the rate. And that is independent, no matter what we do. And that is the dominating factor. Same thing happens in beamforming gain. Yes, that is clear because that is the same as SNR. If we get some beamforming gain and improve our link budget that way, then we again can capture that benefit by increasing the single constellation size. And that means we again have an exponential growth. If we increase the number of MIMO streams, life is better seemingly. Yes, because we're suddenly here in front of the parens and maybe just a linear M is happening. But it is not linear in the rate increase. It is quadratic. Why does it remain to be quadratic? It remains to be quadratic because obviously we have, let's say, 10 times more transceivers for our 10 times more MIMO streams, plus our signal complexity over the air is 10 times more complex. So every transceiver on the receive side sees 10 times more transmitters, and that means the constellation size of what it needs to resolve also increases by 10x. So we have 10 times more receivers that have to have a 10 times higher resolution. So in total, 100x increase in A to D converter power consumption. And we mentioned as we go above 200 megahertz, suddenly we are also in the quadratic regime. This means, what can we do as a physical layer person, as a PHY person? We can increase the SNR to increase the rate. We can increase the antenna gain. We can increase the MIMO streams. We can increase the bandwidth. And the best we can achieve is down here as a quadratic improvement, no matter if we look at the low SNR or high SNR region. And in previous life, since our sampling frequency was below 200 megs, typically we were in the linear region here. And this and technology also gave us this nice 100x improvement, nearly 100x improvement. So life on the ADD converter was great. Now we have a problem. As we increase the data rate, it comes at a large energy cost, and the energy cost is basically what it's the receiver, not the transmitter. It's not the power amplifier. It's the receiving part and in the receiver, the A to D converter, that is really the issue. And if we were to throttle the modem, even if we're not at super high data rate, as we showed initially, if we throttle any of these parameters, we don't get the gain that we need to get. So what can we do? Are we doomed? Is this whole idea of augmented reality, virtual reality, not going to be able to go cellular? And good news is, if we look at networks, they are loaded over time. This is a Southern Manhattan measurement that we did. We used Twitter data, and you can very nicely show that Twitter data is highly correlated with traffic load. And as we also look forwards to 6G and consumer products being basically driving that, that means anything that is around humans. So where humans are, the data will be exploding because an AR system will also be developing the data where the human is. So that's why we anticipate that our Twitter data is really highly correlated with where the data is happening. And it's happening over time in a sinusoidal modal waveform, modulated. And even if we go to shopping centers like in downtown Jakarta, Grand Indonesia, we did some measurements there. You can see it's a sinusoidal waveform. That means our peak is not happening 24/7, but only 10% of the time. That means the sine-modulated traffic gives us a chance to say, if we drive our whole system and design our whole system for peak data rates like we do today, and then throttle it a bit, we're not going to get what we need. But at least 10% of the time, whether this modem is doing something right, but 90% of the time, our modem has this big A to D converter load and this bandwidth load and everything without any purpose. And if you look at what narrowband IoT does, is exactly that it captures this and has a narrowband system, because in that mode, the modem never goes to high data rates. So this concept is not that new, but if you think of it now in a different fashion. Why? Because we're going to have massive MIMO in a very big fashion. Massive MIMO means the data rate over the area that we see today starts not being seen in 120-degree sectors, but pixel by pixel. because suddenly we can see different spots. Today, in a network where we have 100-degree, 20-degree sectors of a base station sector, we sort of integrate over the whole 120-degree, and over the integration of the whole 120-degree, any hotspots that are in there are just integrated, and that's why every sector sort of looks similar. If we, however, look at how the actual cellular data happens, it is much spottier. Yeah, cellular data happens in a very spotty fashion. And again, if you look at this from a Southern Manhattan kind of tweet map, you can see how cellular data is correlated, how it's generated. And you see you have this very spotty kind of situation. And it's smoothed out with our current technology, but with massive MIMO, we will be addressing every single cell pixel. That means we have to look at that. Now, what is the distribution? If we start looking not at 120-degree sectors, but make this smaller and smaller, suddenly it turns out it is a log normal distributed traffic generation over pixels. And as you know, in log normal case, about the 1% here on top, these two curves cross here, the 1% part on top, dominate the total traffic, whereas it's a long tail distribution. So you cannot just cut it off. We know that. Log normal is a long tail, but with a heavy peak sitting up there, that means it is not every modem that is going in peak mode. If we think of the different MIMO beams addressing the different cell pixels, not every beam is in peak mode. It's only a couple of them, maybe 1%. So this gives us a very interesting part. Since it's log normal distributed in space, and today we don't see that because we have 120-degree sectors. We average out these valleys and peaks. However, in 6G, we will see this because we will have this very fine beam resolution of massive MIMO. So we will see this log normal, and that means every single beam should not be operating with the same modem, with the same A to D resolution at a high peak data rate. That's not sensible at all. And in addition, not only can we save energy if we think of this, because only 1% of the beams really need this. In addition, it's sine wave modulated over a 24-hour period. So that if you put these two together, a fully loaded buffer situation, a fully loaded beam is in total a Seldom event, maybe at most a 1% event. And in 99% of the time, or even more than that, we can reduce that. So that means if we revisit this, increasing the data rate comes at a large energy cost. If we make every modem to cover that, we're doomed because Moore is not giving us what we need anymore. We have that end at the 200 megahertz. Throttling a modem just with adaptive modulation encoding is what is done today, doesn't give us a different A to D converter. Yeah, if one resource block has full data rate and other resource block less, that's how we think of designing modems today. That is not the way to do that. But that means in 99% of the beams over time, we don't have a high capacity system. We have, in part, very low capacity system where spectrum is widely available. This is something different. If spectrum is widely available, that means we can switch to a different gear. We don't need to use MIMO or FDM. We can do something completely different. Think of this. We will have beams at 3 a.m. in the morning where we have a spectral efficiency not of 10 bits per second per hertz, but 0.01 bits per second per hertz. Yes, we're in the wideband regime. And what do we know from Shannon? If we're in the wideband regime, This means the spectral efficiency is somewhere far to the left of this. We can operate at very low SNRs and do impulse radio or zero crossing modulation, as is here proposed here, zero crossing modulation. And by doing so, we can dramatically reduce the energy consumption, because then we can use 1-bit ADCs and all these kind of things. So that means, think of it this way, we can cut our spectral efficiency regime into multiple buckets. The bucket where we're like at 0.1 bits per second per hertz, we do impulse radio. We know from our neural network in our body, impulse radio is the best from an energy efficiency point of view. Biology has done this and has learned this. If we increase the data rate, we know zero crossing modulation proposed here is the next best. If we increase more, we know that constant amplitude modulation schemes like CPM, GMSK, whatever, are great. And only then, slowly but surely, that means here we have impulse radio, here we have zero crossing modulation, and then to the right of that, only do we start with what we have focused on the whole last decades. So we should not only design for peak rate, we should look at every single region. Every single beam is operating in a different region, and putting this all into one big box and say, you do have this resource block, you have this resource block, but the whole A to D converter, the whole modem has to cover the full functionality. It makes absolutely no sense. That means building things with one gear in mind and then throttling with adaptive coding and modulation makes no sense. We can even build analog modems for impulse radio and have analog modems sitting there. That means physically implement separate, for every gear, a separate hardware piece sitting next to each other. And I mean, silicon is not the issue. We have square meters of silicon available. And if we look at the peak to average data rate ratio per cell pixel, it is huge. It is enormous. That means the peaks are very high, but the average is much lower. We have the sine wave, sine modulated over time, and the log normal in space, which should give us at least 100x increase in energy improvement. If we assign a different modem for every gear, every mode. This could be, for example, if the spectrum is abundant, we use impulse radio. If it's high, we use zero crossing modulation or CPM, continuous phase modulation. If it's medium, we just use MIMO or FDM. And if it's very low, that means we have very high spectral efficiency. We're really crunching everything out of our spectrum. In these cases, we're willing to waste all that energy. But who cares if we waste a ton of energy in less than 1% of the cases? Yes, if that less than 1% of the cases consumes 100x or whatever is of the power, but we say that's only happening 0.1% of the time, then it is not the issue, because we reduce the power consumption with the massive MIMO, addressing the different cell pixels massively with these other gears. So that's basically the idea. We have these requirements, and the solution is basically come up then with one MAC grid, medium access control grid, that can do both. And if we look at this, this means, yes, we have business, consumer, business, consumer, business, consumer. And to make it consumer ready, it has to be super cost efficient. And to make it consumer ready, energy efficiency and cost, the first thing in cost efficiency is energy efficiency. And here we went from one physical layer, analog modulation, to digital modulation, from 1G to 2G. From 3G to 4G, we went to a new PHY, from SPED spectrum to OFDM. 2G, we had SPED spectrum. 3G, we had SPED spectrum. 4G, 5G, OFDM. So what I'm saying is there is now the moment where we again have to think of going to a different concept. That doesn't mean we don't use OFDM. In the super high data rate gear, yes, MIMO OFDM or Walsh-Hadamard spread OFDM and others are sensible. But we should focus on it only for those parts and make sure that we really come up with a different approach to save the energy of planet Earth. Thank you very much for listening.
Thank you very much, Gerhard, for this quite inspiring presentation. And I think we will let the floor to questions, but just my impressions, my first impressions. What is quite interesting is in your first slides with the chart, the slide where you point out that 6G has not necessarily to multiply to increase all aspects, all features equally. And you mention that reliability, air latency, spectral efficiency have not necessarily to be multiplied, but on the contrary, you insist on increasing energy efficiency, trustworthiness, integrity, and of course maintaining data rate increase as important. So it's important to point that out because and this, to my mind, this illustrates the necessity not to go too fast in defining 6G. On the contrary of all the communications that is beginning to be done on 6G now, because it's a complex concept, and these type of things have to be defined, taking time, putting into consideration what is the most important. And another distinction that is quite interesting is when you compare the different generations between business and consumer, and different between 5G and 6G. And definitely you point out that 5G is mainly business, enterprise, mobile generation, with notably with the verticals, whereas 6G has to become a full consumer generation, and for that the cost has dramatically to be put down and not increased. When in your conclusions, if I can summarize, because it's a full complex demonstration, but you say that definitely the large energy cost will be a challenge if we want to increase the data rate. So, Gerhard, does that mean that even if you propose some solutions to cope with this energy cost, does that mean that we have not necessarily to look after always bigger and bigger data rates, but that some optimum data rates for a certain time at least could be looked after without willing always increasing the data rates? What is your view on that?
Yeah, exactly. So the idea is, yes, that we should increase the peak data rates and should have that available for those cases. But it turns out that in most cases, we're not driving with the accelerator full down. Think of a car and driving on a hilly road and stuck behind a truck. It is way more energy efficient for you to switch to a gear, spend the energy, pass the truck, and after that, cruise along in front of the truck at whatever, 90 kilometers per hour, 100 kilometers per hour at some very efficient gear. So that means we do this in driving too, right? We're not going to be driving in a mode, we're not driving at 120 kilometers an hour in our second or third gear, revved up like crazy, but we're actually using a different gear to maximize the energy efficiency and use exactly the power and the energy that we need. And sort of a little bit in a similar fashion, that's why I call it the Gearbox PHY, is here. That means if we need that data rate, and there is a crunch because others are also doing virtual reality at the same time, then it's fine. Then we'll use it. Then we'll do 100 gigabit per second in that cell pixel, in that beam, and distribute it amongst the different virtual reality users that are in that beam to really give them this data rate. But if that is 0.1% of all beams in the network, it doesn't really make our life such cumbersome to spend that energy in these different points. However, if we design the whole network and all 1,000 beams, every single beam has to carry the burden of this high energy continuously, then we're making a mistake. So that's why, and this is very different from how we have been designing the networks today. You got that on the point. That means we should make sure that we come to realize that this full buffer, super high data rate is becoming less and less the dominant factor. It is becoming spottier and spottier. And that's why we should only provide it there and spend the energy there. And in the other cases, move to complete different gears, different modems, different hardware that are totally optimized at a different point of operation, because that is reality.
Thank you, Gerhard, and that's an important insight of your presentation, and perhaps that goes against some received ideas.
Yes.
So it's quite important, and important at this stage of 6G definition, developments, and so on, in order not to go too fast in conclusions and try to explore all the ways that have to be explored. Another conclusion that has attracted my attention at the end of your presentation, Gerhard, is that spectrum availability is not an issue in 99% of cases. So this is also important, because in this move of more and more spectrum for mobile, and in particular in higher bands, does that mean that we have more to optimize in the future, to optimize existing spectrum, and particularly with perhaps dynamic spectrum allocation and so on, dynamic spectrum sharing, rather than looking at for instance, at the ITU or World Radio Conference, to ask for more and more, always more and more spectrum bands?
So we need to ask for more and more spectrum bands. I truly think that, because our peak rate needs the more and more spectrum. But if you think of it now, if we roll out a network like here, just 50 kilometers away in a very rural, hilly, mountainous part here in Saxony in Germany, the operators put up a tower, and they put up one transceiver with only one single channel. Yes, and it is hardly full. That means if they were having a transceiver that could pick up the full spectrum that they got licensed, they would be operating at less than 0.1 bits per second per hertz, 24/7. This means it would become a super energy efficient system. I could put all that into my link budget improvement, have mega cells that have bigger reach, and I can get the rural area with a nice coverage. However, we're putting base stations in the rural area that were optimized for dense urban systems. And that's why we have a coverage issue. We have a coverage issue for multiple reasons, but that's also one reason why. And we have an energy issue there. And that's why we have a cost issue there. So we could set up a complete different base station out there that would be way more energy efficient, cost efficient, and everything. However, capturing and using all the bandwidth, not only one channel as it is today. And by doing so, having complete different modulations, a different gear, and we wouldn't even implement the urban, super high data rate, expensive gear in those rural environments, and therefore come up with a complete different proposition. Because, as you know, it's not the capex that dominates; it's also the opex that dominates, and the opex, operational expenditures. Today, the energy bill is the dominating factor already in a base station. That means already today we have that issue. And if we go forward, as I showed, it becomes more and more of an issue. And that's why, yes, we do need more spectrum, and we should also use it all over. But think of it, that we have different base stations. One that has four gears, we put it in downtown where the money is earned. One that only has the low gear, we put it in the boonies where we don't need more than the low gear, etc. Still, we can have a gigabit per second with this low gear whenever it's needed, or the medium gear whenever it's needed. So this way we can have a complete different portfolio that is a different concept than we see today.
Quite interesting. It's a nevertheless, so it demonstrates that it's a sort of optimization of means and resources. Or although, as you underline, although we still need to ask for more spectrum
Yes.
in the next World Radio conferences, because we have to cope with the peaks, with the peak needs. So on my side, these were my, of course, many aspects of your rich presentation could be commented. On my side, it's all what I wanted to say, highlighting the fact that 6G consumer, Gerhard, will have as the object tactile internet, and for consumers to be will have to be always super cost efficient. It's perhaps one of the most strong, the strongest aspects of your presentation. Are there some questions from the floor? Sonia, Asif?
So
Have
there is
we?
no question in the question tab box, and I think 107 right now the time. So
We're perfect in time.
yeah,
Great. Then let's keep it that way. All right.
yeah, thank you so much.
So I will thank you very much, Gerhard, and definitely your presentation will need to be cross-examined, to be studied in order to deepen some aspects, and particularly when you demonstrate and this quite interesting comparison between Jakarta and New York. With the curves of traffic, and also quite interesting this correlation of tweets and actual cellular data. So it's quite interesting, because we know the importance of these social networks traffic, and this is quite interesting demo. Thank you very much, Gerhard. This was quite inspiring, and we will now go on. But if I'm not wrong, there is a lunch break. Perhaps the host indicate me exactly at what time we resume for the papers. I've just to precise that we will have now the session 2. Just I remind that this SDR workshop is divided into 3 sessions. Session 1 was with Arzad performance studies with 3 papers. Then we had Gerhard keynote, and we will pass afterwards to session 2, potential applications, that I will chair with 4 papers, 4 presented papers. And then after the tea break, it will be the third and last session on technologies with the two last papers of the day. So perhaps Sonia or Asif, could you indicate me what is the forecast in terms of lunch break and at what time we resume?
Yeah, so this is, I think lunch time has been started, and we can resume at 2:20 p.m. IST for the second session.
Okay, 2:20 IST. So that means it's always difficult to translate because of these 30 minutes in CET. So I suppose it's 9:50 a.m. CET.
Yeah,
9:50.
almost.
Yes, yes.
Yes, sir. It will be 9:50 CET.
Okay, fine, fine. So let's go now for this break, and the host, Asif and Sonia, will manage this time break, and let's resume at 2:20 IST for session two, for papers. Thank
Sure,
you to
sir.
all.
Yeah, thank you so much, and
Thank
thank
you,
you,
sir.
Gerhard, for making me the very good presentations. Thank you, sir. We are just ending now.